Okay, welcome to measurement. This topic is essentially a practical topic, so we'll see how we go. This is all the guide to the notes. So when you look at the learning outcomes, you need to know how to measure things with a few different types of instruments, so ruler, vernier scale, protractor, and so on. The interesting stuff that we'll look at later would be using errors, which is probably one of the most difficult parts. So what we have here is a couple of techniques to remind you of what you need to do to measure properly. First one there, if you're not looking at things straight, you get, remember, you get a parallax error. Okay, the second one there, well, both these cases, they're not measured correctly because you look at where they are starting from. They're not starting from zero, so we call this a zero error. You got to really look for that, especially when you're doing your own practical work. This device here actually helps you out with your parallax error. So the first one is the best one. The second two are not very good. You can see why by looking at the image there in the background. And because there's an image seen in the background, then you're not looking at it straight on. In the first one, there is an image, but it's directly behind the needle. So it tells you, hey, there's no parallax error. Okay, so you need to be able to use two devices here. One's the vernier calipers, one's micrometer. Vernier calipers are good for things about the size of a pen, if not bigger. Okay, so bigger than a pen. Micrometer usually for stuff that's smaller than a pen. The vernier calipers also have these inside jaws, which are great for inside of pipes. So if you had your pipe like that, you could put the jaws inside there, and they actually expand to the inside edge, and it's quite a good way of measuring things. So there's a video there you can look at, and there'll be some videos on the site. But let's look at this example here. First step, we use the main scale. So we use these values here. So that's the first step. Where do we line it up? Well, we line it up with what the zero is looking at. Okay, this zero here is looking at 25, 26 millimeters. Okay, so 26 millimeters. But you can see it's between 26 and 27. So what is that point? Well, we look at this scale here. So this is the 0.1 millimeter scale, and we look for which one is lined up. Okay, it's quite hard to see it on this board. The 6 probably looks the best. The 4 is slightly to the right. 6 is lined up, so that's lined up the best, I think, out of all of them. So looking for one of the values that's lined up with something on the main scale. Okay, in this case, the 6 looks the best, so we'll put in a 6 there and give it a unit. Micrometer, essentially pretty similar, but it's a lot more precise. This is generally a millimeter scale, so you're looking at 1, 2, 3, 4 millimeters there. So let's have a look at it. If you look at this part here, so there's 1. This 1 is going to be cut down into 4. Our ones actually that we will use are not as close as that, but we'll see what they're like later. So in this case, okay, so in this case here, we got a reasonable number here. So you've got to look for what this value lines up with here. Okay, so how does that line up there? And you can see you've got 3.5, 3.75. So it's just a little bit higher than that. And what you do is you then add on the one that lines up. So this will be 3.85. Okay, you must also know how to use a meter ruler, force meter, electronic balance, scales, protractor, and a few others, but we'll look at that later. CRO. Now CRO essentially a device that makes a graph, okay? There's some sort of value in the y, but it's always against time. So you could have something that goes like this, okay? And if let's say this is voltage, well, you could have a 1 volt there, okay? So it could go to 1 volt down to -1 and so on. So that's what you could measure, but generally you use it for waveforms. Like on this screen here, you got that waveform, okay? So you can measure the voltage output from a microphone to see the frequency or period. Okay, two important things. Y calibration. So that's how you calibrate the up and down. Okay, and you decide. So if your waveform is going off the screen like that, you can make the division larger so it fits it in. The other way is this way, which is this one here, the time base. If you get hardly any of the wave like this, then you want to shorten it, so you make the steps larger. So what we've got here is you got your two things. Time base tells you divisions and the vertical volts per division. So in this case here, this thing is set to, I think it's 1 millisecond per division. That's what it tells you there. So each of these divisions, each of these lines along this way is 1 millisecond. So if we have 16 lines across for one period, then it must be 16 milliseconds for that period. And remember, F equals 1 over T to find out your frequency. Defining analog and digital. To do that, you can look in the dictionary and so on, but let's just state what we might know about it. You could say that analog is a continuous spectrum of values. There's no sort of jumps between values. It's just a continuous spectrum. On the other hand, digital, it could just be 1 and 0 like you do in digital electronics, but it could also be like a digital clock where one of the numbers will go 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. So that's also a digital. There's defined numbers there. Now, uncertainty. All measure values are never exact. All measure values have some uncertainty, and uncertainties are also called errors. So whenever you measure something, no matter what it is, you're not going to get it to an infinite number of decimal places. You know, no device is that good. So one important thing you need to remember is if you have a fraction, don't leave it as a fraction, because that fraction is implying an infinite number of decimal places. So you have to always round your value. Estimating uncertainties. In general, the uncertainty in a reading is equal to the smallest scale. So let's say you had a meter ruler. The smallest division will be 1 millimeter. That's what we could use there. I mean, another way of looking at it is you could vary by 0.5 millimeter on each side of that line, but on a meter ruler, you're actually doing it at two ends of the thing you're measuring. So in total, it's 1 millimeter. The strange one is a thermometer, which you can guess it by 0.5 millimeter. Okay, as the needle goes up, you can measure find it by 0.5 millimeter, and the bottom's perfect. So the error on a thermometer is half a degree, not millimeter. Now, what we got here is a example of a measurements of some wood. Okay, and the person has measured it 1, 2, 3, 4, 5, 6 times, okay, to get a measurement. Now, what we might do is, let's see if I can find the calculator on here. Oh, it might be over here. Here we go. It's gone missing. There it is. Sorry about this. Put that there. Done. Okay, so let's have a look at this calculator. So, let's put in some values. So I want 4.90 plus 4.95 plus 4.92 plus 4.96 plus 4.93 plus 4.91. And see what that equals. So there's 29.57. How many of them are there? There's 6, so let's divide that by 6. And we get 4.9283, blah, blah, blah. Okay, so quite a few values there. But we're going to round it. So what is the length of the block? It's going to be 4.93. We're going to keep it to the same number of sig figs as given to us in the question or in our original measurement. So the length of the block is equal to 4.93 centimeters. Now we could actually say that there is an error in this. So there is a variation. So we actually, if we got 4.93, we could go up and down by a certain amount. We could go up to 4.96. So we could go up 3, okay, up 0.03 in fact, and we could also go down from 4.93 to 4.90, so we could also go down 0.03. So our error will be how much we go up and down. Okay, so using some devices, I can just tell you what the uncertainty is. What's the sensitivity of a micrometer? Usually it's to 0.01 millimeters. Okay, what's your uncertainty? It's going to be generally the same. Okay, digital stopwatch, 0.01 seconds. And usually you can say that the uncertainty is the same, or if you want to look at human error, okay, which is like reaction time, then it's more about 0.1, okay, or 0.2 even. Electronic balance, usually 0.01 grams, okay, so it's going to be plus or minus 0.01 grams. Depending on the device, some of ours might be 0.1 grams. So you have to actually look at what you're measuring. Thermometer, this is the one that is 0.5 degrees Celsius, but yet again, it all depends on the device. Which of the below is the best representation of the length of the pencil and state why? Okay, if you said 10 centimeters, you'll be wrong. Because if you said 10 centimeters, then you're actually saying that where you measure here, that there is no millimeter divisions. Okay, 10.00 centimeters will be wrong because you're saying that we're measuring to the 0.1 of a millimeter, which is not easy on this ruler. So the actual one should be 10.0 centimeters. You have half a millimeter error at each end, and that takes a total error of 0.1, and we are measuring to that millimeter. Systematic error, okay, so using the definition, it's an error that comes up all the time, okay, so it's a repeated error. It doesn't vary the number of times you do it. Can it be reduced? Okay, you can't reduce it by doing the experiment over and over again. Some examples of the zero error. If you start off by being wrong by 1 millimeter in your measurements, every measurement is going to be off by a millimeter. Reaction time, not rhyme, time, okay. Reaction time is usually a fixed value around about 0.2 seconds. Faulty scale could also give you that. However, random error is one that fluctuates. So each is just a natural occurrence of error. Okay, can it be reduced to some extent? Okay, usually 2 repeats would fix it. Whoops. Okay, so usually 2 repeats will fix it. Example is reading a scale. So there's always going to be some variability in how you read scales. A reading which changes with time, counting oscillations, reading a scale from a wrong position. Precision accuracy. Okay, these 2 words are commonly misinterpreted in English language, so it makes things difficult when we're looking at it now. Essentially, the number of significant figures quoted indicates the precision of your measurement. Okay, readings could be precise due to the type of instrument used, but may not be accurate. Okay, so you might be using a micrometer, but you may have a zero error, which means you're not accurate. So accurate is concerned with how close the measurement is to the true value. So if you compare the meter ruler to a vernier caliper is more precise. More sig figs, it can measure a smaller size. But you can have accuracy troubles with both, where you are not near the true value. So a micrometer screw gauge with a zero error will be precise, but not accurate. So looking at the distribution graphs, okay, so we have here a series of measurements, okay, so series of results that you could get. It could be time, so you're doing, like, let's say we do one swing of a pendulum 50 times, and you get a time on the x-axis and the number of hits of a certain time up the y-axis. In this case here, the t is the true value. And you can see that we're actually quite close to the true value with the majority of the measurements. Okay, so we can actually say we are accurate. But in this case, the actual spread sideways is quite bad, so we're not very precise. We should be using a better instrument to get a smaller spread. This one here, not much spread, so we're precise, and we're a majority of stuff is above the true value, so we're accurate and precise. This one here, we're nice and precise, there's not much of a spread, but we're nowhere near that true value, so we're not accurate. This one here, got a big spread, so we're not precise, and we're not above that true value, so we're not accurate. Okay, so that's something you need to remember. Now we're getting into the uncertainty phase, nearly done. So actual uncertainty is the uncertainty of the thing you're measuring. So let's say you measure something with a meter ruler. You might get 0.5 plus or minus, 0.51 plus or minus 0.01 meters. Okay, so what's the uncertainty? Well, that's actually a centimetre, so we should actually really put another zero there and make it a millimetre. Okay, so 0.510 plus or minus 0.001. What is your actual uncertainty? It's that thing there. Okay, so your actual uncertainty is your actual measured uncertainty. Okay. Fractional uncertainty is your actual divided by your measured value. Okay, so for example, if you had 1 millimeter, okay, and you measured 0.510, well, working out tells you the fraction of your measured value that your uncertainty would be. So it could be 1/20th, 1/30th is your fractional uncertainty. What sounds better is a percentage. So all you do is you grab your fraction and multiply it by 100. Okay, so it's actual uncertainty over measured times 100. And so that might tell you that you've got an error of 10% in your measurement. Okay, you could be out by 10%. So there's an example here. You've got 2.34 plus or minus 0.01 centimetres. Okay, so actual uncertainty in this case is 0.01 centimetres. Your fractional, where you're going to do 0.01 divided by 2.34. Okay, and that tells you some sort of fraction. Which one that sounds better is the percentage. So you get that multiplied by 100. Okay, and you get 0.43%. So we could be out by 0.43%, which is actually pretty small. Now when you plus, minus, multiply, divide, the combination of the uncertainties means that your final value will also have an uncertainty, and it could be varying. So what we're going to do is look at how we do it. For adding and subtracting, all you have to remember is you just add the actual uncertainties. So for example, we want to find the difference between the two speeds at y and x. So let's do y minus x. So what is the actual calculation? It'll be 4.5 minus 1.0 equals 3.5. Okay, so that's meters per second. Now what's your error? You're going to add the two uncertainties. So it's going to be 0.1 plus 0.5. So your uncertainty in the end is actually equal to 0.6. So what we're actually going to write then is 3.5 plus or minus 0.6 meters per second. Now the last bit there says that we round the final uncertainty to 1 sig fig. So that's already 1 sig fig there, okay? And then we round your final measured value, your final calculated value here, 3.5, to the same decimal place. In that case, it's 1. Which device is the most precise? Okay, well, it's the one with the smallest uncertainty, usually, is the one with the most precision. So multiplying and dividing, this is the complicated one. What you're going to do first, you're going to calculate the real values. In other words, if it's 2 times 3, well, you do that. You do 2 times 3. Add together the percent or fractional uncertainties of the original measurements. That's the most important. No matter if you're dividing or multiplying, you always add together the percent or fractional uncertainties. Then you find out how much the total percent or fractional uncertainty from 2 is of the real calculated value. So let's say you find that you have a 10% error in total once you add all the percentages together. You get 10% error, and you calculate your real value and you get 4. So then you're obviously going to have a 0.4 error at the very end. Okay, so mass of the stone is found to be that, 78.4 plus minus 0.2 grams, and its volume is found to be that. So let's work out what the actual density is. Density equals mass over volume. So that's going to be 78.4 divided by 22. Okay, so we'll grab a calculator. So 78.4 divided by 22. That makes 3.56. Grams per centimetre cubed. Okay, now let's work out the percent uncertainty. So what's the percent uncertainty in the density? So percent uncertainty in the density, we're going to do 0.2 divided by 78.4. Now you need to write out all this in full, times 100. Okay, so let's work out what that is. Go to the calculator again. So we're going to do 0.2 divided by 78.4 equals that, times 100, and you get 0.26%. Okay, now let's find the percent uncertainty in the volume. So in this case it's going to be 2 divided by 22 times 100. Hope I'm getting mistakes, but I'm sure someone will check through this. So what was that again? Let's have a look. 2 divided by 22 equals that, times 100. So we got about 9.09%. Oops, sorry, keep doing that. 9.09% error in the volume. Okay, that makes about sense. If you have a look at that, it's almost a 10% error. So total percent error is equal to the two added together. So you grab your calculator again. Let's do 9.09 plus 0.26. And you get 9.35. Okay, now, so that means we've got a 9.35% error in 3.56. So let's find out what that actually is. So grab our calculator. How do we work out that? Well, you divide that by 100, and then multiply that by what we're looking at, which is 3.56. So it's a 0.33 error. Okay, so we've got 0.33 grams per centimetre cubed error. Now, remember the rules. First one, around about number 5, I think the rules are. Let's have a look. Just can't remember. This one here. Round this calculated actual uncertainty found in 3, I should write the, to one significant figure. So, this should be 0.3, because it's one sig fig then. And then you're going to round your final calculated value in the same to the same decimal place as the uncertainty. So that's 1 dp. So this must also go to 1 dp. Okay, there's your final result. This one here we'll do in class, but be aware that a v squared, what does a v squared mean? It actually means v times v. Okay, so if you work out the percent uncertainty of 1v, okay, you add it to that one's percent uncertainty. Okay, well, what's a quicker way of doing that? Well, let's just say 2 times the percent uncertainty of v. Okay, so maybe we'll look at that in class.